Hey, Dr. Ramey here again with another video tutorial. This one on how to calculate the minimal inhibitory concentration using a broth microdilution assay. So let's dive right in. These assays are typically done using a 96 well microtiter plate like the one shown here. What we do is do a serial dilution of the antibiotic so that the concentration decreases in wells from left to right. So you have the highest concentration of antibiotic in well A1, and then the concentration is lower in every well, so the lowest concentration is in well A10. Wells in columns 11 and 12 are control wells. In column 11, those wells there is no antibiotic, and then in column 12, these rows, they are not inoculated with bacterium. During incubation, if the bacterium grows, then presumably the bacterium would have some level of resistance, and we can calculate the minimal inhibitory concentration based on the lowest concentration of antibiotic where there's no growth. Like you can see in this well here for antibiotic Z, this is the lowest concentration of this antibiotic that prevented growth of this isolate. So whatever that concentration is would be the minimal inhibitory concentration. So let's walk through this one step at a time. Initially we would collect a sample from a patient that has a bacterial infection or disease, and that sample would be cultured, and the bacterial pathogen would be isolated so that a pure culture could be made for further testing. So we would suspend colonies of this particular bacterium in either sterile broth or maybe saline, and then a standard suspension of that would be made to match a 0.5 McFarland standard. And in doing so, we are standardizing the concentration of bacteria that we are going to use in the assay. So then to set up our microtiter plate, each well we would add Mueller-Hinton to each of the wells, Mueller-Hinton broth. And then rows of wells are prepared with serial dilutions. Typically these are twofold dilutions of the antibiotic that we're testing. Usually we would test more than one antibiotic, and this would create a range of decreasing concentrations. Again, the concentrations of the antibiotic are going to decrease from left to right. And again, the wells in columns 11 and 12 over here are the control wells. So in column 11, those wells do not have any antibiotic, but bacteria will be added, so those wells will be inoculated. In row 12, there's no antibiotic, but there's also no bacteria added, so those wells are not inoculated. Then we would add a standardized volume of the prepared bacterial inoculum to each of the wells containing the antibiotic dilutions and the growth control wells, so those would be the wells in column 11. We would incubate that plate, typically between 16 and 24 hours at a temperature of 35 to 37 degrees Celsius to allow growth. And then we would evaluate that plate for growth, looking for turbidity in each of the wells. So the MIC is identified as the lowest concentration of antibiotics in which there is no visible growth. So again, this is an example of a well where this is the lowest concentration of antibiotic Z that prevented growth of this particular isolate. So whatever the concentration is here, and that's what we have to figure out, would be the minimal inhibitory concentration, or the MIC. This of course is assuming that the control wells end up as expected, which would be that the wells inoculated in column 11, we see growth because there's no antibiotics there, and then wells in column 12, we do not see growth because those wells were not inoculated. So the determined MIC value for each antibiotic is compared to established clinical breakpoints. And a breakpoint is a predefined concentration threshold of an antibiotic, typically determined by the Clinical and Laboratory Standards Institute, or CLSI. So we can see that these are examples of some CLSI MIC breakpoints for some common antibiotics, commonly used antibiotics here. And using those MIC breakpoints, calculated using the microbroth dilution assay, we can establish whether a particular isolate is susceptible to the antibiotic, intermediately susceptible, or resistant to the antibiotic. So for example, if we calculate a MIC value for ampicillin to be 6 micrograms per microliter, well, 6 is less than 8, so anything 8 or lower is considered susceptible. So we would say that isolate is susceptible to ampicillin. And of course, that information helps guide appropriate antibiotic therapy for the patient. All right, so here's an example here where I'm using the same plate here that I've used in previous slides. And if we look at, again, antibiotic Z, we can see that this is the well where the lowest concentration of antibiotic prevented growth, and that's calculated at 2 micrograms per mil. So for antibiotic Z, 2 micrograms per mil rests within this intermediate range here. So if it was 0.5 or less, it would have been sensitive. If it was 4 or greater, it would have been considered resistant. Now for antibiotics X and for antibiotic X in this case, there was no inhibition all the way up to 128 micrograms per mil, so we can't calculate the MIC value for that particular antibiotic. But if it's anything greater than, equal to, or greater than 32, then it would be considered resistant. So although we can't calculate what the specific MIC is for antibiotic X, we can establish that it is indeed resistant to that particular antibiotic. So let's do a couple of practice problems where we do all of the calculations now that we know how the process works. So let's say that you dilute a stock concentration of antibiotic X, and so it's at 38.4 milligrams per mil, and you, by adding 10 microliters of the antibiotic to 990 microliters of Mueller-Hinton broth to make a working stock. So we've added 10 microliters of the antibiotic at this concentration, and we've used 990 microliters of Mueller-Hinton broth as the diluent. So this will make our working stock. So what's the dilution factor and what is the working stock concentration in micrograms per mil of antibiotic X? So notice that we're switching here from milligrams per mil, which is the stock concentration given, to micrograms per mil here. So we want the working stock concentration to be in micrograms per mil. So what is the dilution factor? Well, the formula for dilution factor is the volume transferred. This is just a simple formula here for dilution factor. So volume transferred over total volume. And of course, total volume is the volume transferred plus the diluent volume. So the volume transferred is 10 microliters, so right here. And then 10 plus 990 is 1,000 microliters. That's the total volume. So this is a 1 over 100, or in scientific notation, a 10 to the minus 2 dilution factor there. And so we figured out what the dilution factor is, 10 to the minus 2. Now we want to figure out what's the working stock concentration. So final concentration, I'm just going to put final in brackets to indicate final concentration, is the original concentration times the dilution factor. So that would be, the original concentration is 38.4 milligrams per mil. I'm going to leave the units off for a moment. Times the dilution factor, 10 to the minus 2. So 38.4 times 10 to the minus 2 is 0.384, and then that's milligrams per mil. But that doesn't give us the answer we want because it's got to be in micrograms per mil. So we need to convert 0.384 milligrams per mil to micrograms per mil. You would need to know that 1 milligram equals 1,000 micrograms. Or that would be the easiest conversion. Or if you weren't sure about that, as long as you knew that 1 gram equals 1,000, I'm going to use scientific notation, milligrams, and that 1 gram equals 1,000,000 micrograms, you could use that as well. So if you knew this, then it would look like this. 0.384, this is milligrams per mil, times 1,000 micrograms over 1 milligram. Now the milligrams cancel, and 0.384 times 1,000 is 384, and that's micrograms per mil. And that is the answer we seek. So this is 384 micrograms per mil. Now, if we were instead going to use these two conversion factors, we'd start out the same, 0.384 milligrams per mil, and then we could first convert that to grams per mil. So we know that 1 gram is equivalent to 1,000 milligrams, and then we could convert from grams to micrograms because we know that 1,000,000 micrograms is equivalent to 1 gram. So let's check. See, the milligrams cancel, grams cancel, we're only left with micrograms. Okay. Here we have 1,000,000 divided by 1,000, so we subtract the exponent here to make that. That would be 10 to the 0, so that's just 1. 10 to the 0 is 1. So then we have to subtract that exponent here too. So 6 minus 3 is 3, so this becomes 10 to the 3rd, or 1,000. So now we're back to 0.384 times 1,000. So that's 384, and then micrograms per mil. So you get the same answer, just a little bit, and this is an extra step there. But if you're not sure about that, then you can always use those. Okay, so now that we have that information, 384 micrograms per mil, so that's our working stock. So I'm going to write that in here so we don't forget it. 384 micrograms per mil. It says after adding 90 microliters of Mueller-Hinton broth to all wells in row A, so here's row A, of the microtiter plate, you add 90 microliters of the working stock antibiotic X to well A1. So all of the wells here says all of the wells here in row A, so that would be A1 through A12. We've added 90 microliters of Mueller-Hinton. And then to row A1, we've added 90 microliters of working stock antibiotic. Okay, so 90 microliters of antibiotic. So that gives us 180 microliters total. Now, going back to our dilution factor, which is volume transferred over total volume. Well, we transferred 90 microliters of antibiotic into 90 microliters of Mueller-Hinton, so that's a total of 180 microliters. So this is a 1/2 dilution. You could say if we wanted to call this a 0.5. So also if we want to determine what the antibiotic concentration is, the final concentration again is the original concentration times the dilution factor. So the original concentration is 384 micrograms per mil times 0.5. So that is 192 micrograms per mil. So this in A1 is 192 micrograms per mil. Then we mix A1 and transfer 90 microliters of A1 to A2 and continue that process until well A10. So well A11 is not going to get antibiotics, so I'm going to go ahead and write 0 there. So every transfer here creates another 0.5 dilution factor. Every single one, 0.5, all the way down. All the way down. Okay, so that means that every time we do that, we are cutting the concentration of antibiotic in half. So if this is 192, then well A2 is 96, and well A3 is 48, and then A4 is 24, then A5 is 12, A6 is 6, A7 is 3, A8 is 1.5, A9 is 0.75, and A10 is 0.375. So we have, and also to be clear, it says you're going to discard 90 microliters from well A10. So after you do all of these transfers, you're going to end up with 90 microliters left that you're not going to put into well A11. So you're just going to discard that 90. So all the wells are going to have the same volume in them. And now we know what the concentration of the antibiotic is in each of the wells. So now we finished setting up the 96 well plate by inoculating each of the wells A through 11 with the bacteria. Remember, A12 is the no bacteria control well. We incubate that plate at 35 degrees for 24 hours, and then we observe turbidity in wells A7 through A11. Okay. So the well that has the minimal inhibitory concentration is A6, and we've already calculated the concentration of antibiotic X in well A6 to be 6 micrograms per mil. So using the MIC breakpoints from a CLSI chart here, we see that 6 is less than 8, so that we can say that this bacterium is susceptible to antibiotic X. All right, let's try another one. Okay, so in this case we've got a stock concentration of 6.4 milligrams per mil of 3 different antibiotics. So we're going to be testing antibiotics X, Y, and Z. We add 10 microliters of those antibiotics to 90 microliters of Mueller-Hinton broth diluent to make a working stock. So what's the dilution factor, and what is the working stock concentrations in micrograms per mil of the antibiotics? Alright, so the dilution factor is again the volume transferred over the total volume. For each of these, we're transferring 10 microliters into 90 microliters of diluent, so that's a total volume of 100 microliters. So this is a 1 over 10 or 10 to the minus 1 dilution factor here. So that answers that question. Now what's the working stock concentration of each of these antibiotics? Well, they're all going to be the same. So again, the final concentrations are the original concentrations times the dilution factor. So that's 6.4 milligrams per mil times 10 to the minus 1. So that's 0.64 milligrams per mil. But we need that in micrograms per mil, and we know that 1 milligram equals 1,000 micrograms. So we're going to set up our dimensional analysis problem to do this conversion. So we've got 0.64 milligrams per mil. We're going to multiply that times 1,000 micrograms over 1 milligram. Milligrams cancel. 0.64 times 1,000 is 640 micrograms per mil. So that answers the second question. So all 3 of these antibiotics now have a working stock concentration of 640 micrograms per mil. So I'm going to write that in here so we don't forget it. So here's our 96 well plate. We're going to be testing, it looks like 3 antibiotics this time. X, antibiotic Y, and antibiotic Z. So it says we add 50 microliters of Mueller-Hinton broth to all the wells in rows A, B, and C. We need 3 wells, 1 well per antibiotic. Then we add 50 microliters of working stock antibiotic X to well A1. So this well right here, 50 microliters. And then we're going to mix and then transfer 50 microliters to well A2, mix, and then 50 microliters to well A3, mix, and so on and so forth until we get down through A10. We are not going to put any antibiotic in wells in column 11, so I'm just going to go ahead and write a 0 there. So we need to figure out what the concentration is here in A1. And by the way, we're going to do the same exact thing with antibiotics Y in row B and antibiotic Z in row C. So since the working stock concentrations of all 3 of these antibiotics are the same, the concentrations of all 3 in each of the columns and the wells in each of the columns is also going to be the same. So let's just figure out what the concentration is based off of row A, and it'll be the same for rows B and C. So we started off with 50 microliters of Mueller-Hinton broth in all of the wells. Then we added 50 microliters of the antibiotic to well A1. So that's 50 microliters into 50 microliters of Mueller-Hinton, so that's a total of 100. So again, our the dilution factors here are 1/2 or 0.5, so meaning that we're going to cut the concentration of the antibiotics in half at each of these steps. So in wells A1, the starting concentration is going to be half of what it is in the working stock concentration. So the final concentration, so this will be the concentration in A1 in this case, in well A1, is the working stock concentration times the dilution factor. Well, the working stock concentration is 640 micrograms per mil. The dilution factor is 0.5. So 640 times 0.5 is 320 micrograms per mil. So the concentration here in all the wells A, B, and C in column 1 is 320 micrograms per mil. And then every well down to column 10, it's going to be 1/2 of the previous well. So 320 divided by 2 is 160. 160 divided by 2 is 80. Then 40. Then 20. 10. 5. 2.5. 1.25 and 0.625. So there are the concentrations of our 3 antibiotics in all of those wells in rows A, B, and C in columns 1 through 11. So now you finish up, you add the bacteria, so you inoculate the wells in columns 1 through 11, incubate the plate 35 degrees Celsius for 24 hours. What is the MIC? And is the bacterium susceptible, intermediate, or resistant to the antibiotics? So it just says antibiotic X here. We're going to calculate what it is for all 3 antibiotics. So let's look at antibiotic X first. The control wells look good, so we always have to check that first. So it looks like we have a little bit of growth in A4, little bit. So we're going to go to well A3 and say that is, well, A3 contains the MIC concentration, which is 80 micrograms per microliter. So for antibiotic X, 80 is well above the 32 threshold, so it is resistant. So the bacterium is resistant to antibiotic X. So let's look at antibiotic Y. So that's in row B here. Looks like we have no growth in well B8. So that contains our MIC concentration of 2.5. Looking at our MIC breakpoint chart here for antibiotic Y, 2.5 is below the 5.5 breakpoint there. So the bacterium is sensitive to antibiotic Y. And then for antibiotic Z, it looks like there might be a little bit of turbidity right here in well C2, so we're going to say that well C1 has the MIC concentration of 328 micrograms per mil. So for antibiotic Z, 328 is way above the 4 micrograms per mil threshold. So again, the bacterium is resistant to antibiotic Z. I hope that this has been a helpful tutorial. This is Dr. Ramey signing off.